Hey, our first talk of this week is by Zhibo Yu from Penn State, who's going to present dust obscured galaxies in XMM SERVS field.
Hi everyone. My name is Zhibo Yu. I'm currently a PhD student at Penn State. Today, I'm very happy to talk about my recent studies of dust obscure galaxies. So here is the outline of my talk. So I will first give some brief scientific background. Then I will talk about how we select our dust obscure galaxies or dogs. Then I will present their multivalence properties. And finally, I will try to address the scientific question, are those dogs created by mergers as proposed by previous simulations? Here is my introduction. So how do the central supermassive black hole co-evolve with their host galaxies has always been a central topic in extragalactic study. For example, to explain those luminous quasars, people propose the so-called merger-driven galaxy supermassive black hole co-evolution framework. Under this framework, major mergers among gas-rich galaxies can trigger strong star formation. In the meantime, the gas and dust can also fill the central supermassive black hole, allowing them to be observed as an AGM. Then radiation-driven outflows can sweep out the surrounding gas, and then this obscured AGN can become an unobscured quasar. In the meantime, the outflow and feedback may also suppress the star formation. And in the middle of this evolution sequence, those galaxies are thought to be very dusty, and they may be very important link in understanding the evolution of the co-evolution between black holes and galaxies. To study those dusty systems, it is very valuable to have wide field IR telescope because the dust emissions can be directly traced by IR observations. There are many definitions and selections of different types of dusty systems, and here I can name a few. First is so-called dust obscure galaxies, which is the main topic of my talk. The selection was made by Spitzer, and the selection was quite easy. You just apply a simple optical to IR color card, where the bracket 24 is the photometry at 24 micron. You simply apply a color card and the IR flux card, then you should be able to select a large sample of those sources because you would anticipate those dusty systems will be heavily obscured in the optical and have strong dust emission. And then similarly, using WISE, there is another population called IR bright dogs, and their selection has the same spirit. You apply a color card and an IR flux card. Similarly, using WISE, a more extreme population, and many people have been talking about that, is the so-called hot dog. To select hot dogs, originally they used a so-called W1, W2 dropout technique, where they require a significant detection in W3 or W4 band, but there's almost no detection in W1 and W2 band. Such dropout technique will try to select sources with very steep mid-infrared spectral energy distribution. Then going back to what I previously introduced, the merger-driven galaxy co-evolution framework, simulations of major mergers have suggested that in a post-merger phase of merger, the observed quantity of the merged systems would be very similar to the properties observed for dogs. So people postulate that the origin of those dust obscure galaxies may be mergers. However, observationally, there are some discussions. For example, first I introduce the observational result for those most extreme hot dogs. For example, on this plot, they show the X-ray luminosity versus the X-ray column density, and they also show the joint constraint for those extreme hot dogs. And then they compare their results with those luminous type 1 quasars. They find that those extreme hot dogs tend to have a similar X-ray luminosity, but they have slightly higher obscuration level, which supports the merger-driven coevolution framework. There are also other observational studies on other populations. For example, the heavily obscured AGNs. Those sources are somewhat similar to dust obscured galaxies, but they have less extreme colors. And people look at combined evidence, for example, from X-ray obscuration, host gaseous properties, and their morphologies. They find that those heavily obscured AGNs may not be created by mergers. However, in terms of my study on dogs, the studies right now are still inconclusive, as those results on their dust properties can be explained by both by models either driven by mergers or secular processes. So in my study, I will try to answer this key scientific question: do dogs fit into the merger-driven coevolution framework? As I shown earlier, the selection criteria for dogs is quite simple. You can easily select a large sample of dogs. However, the most important thing is that the source characterization is usually not good. For example, originally they select over 2,600 dogs in NOAA Deep Wide Field survey, but they were only able to carefully study 86 of sources with available SPECZ. On the other hand, take the example in Cosmos. Riguccini et al. They select over 180 dogs. The Cosmos field has good multivariance coverage, but it's a relatively small field. So the sample size is also limited. So on the so in my talk, I propose to study dust obscured galaxy in the XMM SERVS field. To give a brief introduction, XMM SERVS is the largest medium depth X-ray survey, reaching a depth about 50 kiloseconds, and those fields are with good UV to radio coverage. This survey contains three primary LSST deep drilling fields: wide change deep field south, ELIAS S1, and XMM LSS. There are also many other foundational work, including photosys, LCD fitting, and AGN classifications. So studying dogs in XMM SERVS could provide us a large search volume and with good source categorization. Here's a simple selection results. We apply the same selection criteria as they et al. So we apply a optical to IR color card and a IR flux card, and those dogs are shown on the upper right region, and those typical gases in XMM SERVS are shown in this gray contour. So by construction, dogs show rather IR to optical color and higher IR flux. After this simple step, we would end up with 3,770 and 38 dogs as our full sample. But although right now we can have a large sample, as I said before, we need to make sure our sources have a good characterization, like they have reliable redshifts. So we assess the photosy quality for our sources. Unfortunately, we don't have too many sources with SPECZ because our dogs are generally faint in the optical band. So not many dogs have good SPECZ, but we still make some comparison between photosy and SPECZ, and you see there's large outlier fraction. So we decided to apply an additional photosy quality card called QZ good. So basically, the small the value, the more reliable the photosy is, and we take a nominal value of QZ less than 1 and so them as a reliable photosy. And as you can see that after applying this photosy quality cut, the outlier fraction is greatly suppressed. So we decide that we need to define an additional so-called core sample for our dogs have available spec Z or with a photosy quality indicator less than 1. And then next part, I will introduce the multivalence properties of our sources. The first thing we want to do for our dogs is to have the SED fitting results. Their SEDs were fitting using XCGAL, where we also include the X-ray photometry to help constrain their AGM properties. And immediately from that plot, for example, those 2 sources have best fit Galaxy model, while the other 4 they have best fit AGM models. Immediately from the results, you would see that that even dogs are called dust obscured galaxies. They may not really be so dust obscured in terms of their in terms of their galaxy component. For example, take this source for example. At for example, rest frame 8 micron, you can see the AGN contribution is significant, which means that the dogs is actually a heterogeneous population where you could both have a heavily obscured galaxy, or you can have some AGN contribution, so that those AGNs can be more easily be selected as dogs. And also from our SED fitting, we can also obtain those host gas properties like their stellar mass and their normalized star formation rate. By normalized star formation rate, I mean the star formation rate divided by the corresponding star formation rate main sequence. So we can look at whether dogs are on the star formation main sequence or above or below that. Here is a more general plot where we plot the redshift versus the bolometric luminosity of our sources. So our dogs are shown in blue and orange, where the blue sources are X-ray detected dogs and orange are X-ray undetected. We also plot other sources for comparison. For example, here, those are the most extreme hot dogs shown in red. And for those gray ones, they are just typical X-ray AGNs in XM SERVS. And if you look at the redshift distribution and bolometric luminosity distribution, our dogs generally are between redshift of 1.5 to 2.1. That is because of the color selection criteria. They they tend to select more sources at that redshift range, and the bolometric luminosity is above 10 to the 12 solar luminosity that already place our dogs among those ULERGs. And here I show the observed X-ray luminosity for our 174 dogs detecting X-ray, and their median X-ray luminosity reaches 10 to the 44.3. Such a high value basically only tells us that all of those X-ray detected dogs, they have to have some AGN component. For those X-ray undetected ones, we also use use X-ray stacking to try to have an unbiased view of them. So visually from those stacked image in those 3 bands, you can already see some signatures there. And we did more quantitative analysis. We find that we have significant detection in all 3 bands. And those X-ray signal may also from X-ray binaries or hot gas. And we did use the scaling relation to estimate their contribution. And we find that the stacked X-ray luminosity is about 3.4 times of that estimate for X-ray binary and hot gas. And basically also means that the origin of those X-ray emission from X-ray undetectables is also highly contributed by AGNs. Then we try to look at their X-ray obscuration. Since most of our sources do not have enough counts for very detailed X-ray spectral fitting, we use the hardness ratio to estimate their column density. So on that redshift hardness ratio plot, we plot curves with the column density of 10 to the 22 and 10 to the 23. By comparing the location of our sources and the curves, we can have an estimate of their column density. And here we plot the column density versus the X-ray luminosity for our X-ray detected dogs, and those are shown in blue. And for comparison, we show dogs studied in other studies like in yellow, and those extreme hot dogs in red. Basically, we find our sources occupy a wide range of X-ray luminosity and column density. That also suggests a heterogeneous nature of our sources. Apart from their multiple from SED fitting and X-ray property, we also look at their radio property. Here we look at their 1.4 gigahertz luminosity versus the IR luminosity. And here the dashed line shows the IR radio correlation for star-forming galaxies. Basically, we can apply this relation and try to look at whether there's any dogs that show elevated radio emission, so we can find the radio AGNs among our sources. And those radio agents among our sources are shown in those circles. And we further studied their radio properties, like their radio spectral slope, and you look at whether they have X-ray detection. We find that our dogs with radio access, they do not present distinctly than typical radio AGNs. In the final part, I will try to address the key question I mentioned earlier. Are dogs created by mergers under the merger-driven galaxy supermassive black hole coevolution framework? So under this coevolution framework, we should expect dogs show different supermassive black hole acceleration compared to typical galaxies. Here we define the so-called specific black hole acceleration rate. You can regard this as a proxy for Eddington ratio. And we did a very simple calculation where we just assuming a typical constant lambda naught, where this lambda is to mimic the Eddington ratio. And by looking at the X-ray property from both the X-ray detected sources and those stacked X-ray luminosity from X-ray undetected sources, we could have an estimate of their AGN fraction. So in the end, we find that the AGN fraction of our dogs is around 2% to 20%. And that value is similar to the typical galaxy population at a similar redshift of 2 and stellar mass. And then we look at whether our dogs they have a stronger star formation than typical galaxies, because under that coevolution framework, dogs are at the peak phase of star formation. What we did is we compare our X-ray detected dogs with those typical X-ray AGNs. The way we do that is that we first control for our two samples, control the redshift and the X-ray luminosity for those two samples, and we compare their stellar mass, their normalized star formation rate, and the column density. We find that our X-ray detected dogs generally have a higher stellar mass and higher column density, but they do not they do not show much stronger star formation. If we look at their normalized star formation, that basically means they are not more star bursty compared to those typical X-ray AGNs. One interesting additional analysis is that what if we further control for their stellar mass? And here we further control for the stellar mass and also control for the redshift and the X-ray luminosity. Still, we find that those X-ray detected dogs, they have a higher column density, and their normalized star formation rate is still similar to those of typical X-ray AGNs. So from those comparison results, we think that rather than in a post-merger phase as proposed by simulations, we think that X-ray detectors may be more similar to extreme type 2 AGNs, where secular processes may be more relevant to their formation. Here are several arguments. First, type 2 AGNs typically show stronger optical obscuration that can contribute to the selection of dogs. Also, it has been found that the type 2 AGNs, they have slightly higher stellar mass compared to like type 1 AGNs. If we consider that galaxy-wide dust also contributes to their obscuration. And since more massive gases can tend to have more dust, that can explain why type 2 AGNs have a slightly higher stellar mass, which is consistent with our results for X-ray detected dogs. And then type 2 and type 1 AGNs, they also tend to have similar star formation rate distribution. And that can is consistent with our results that our X-ray detected dogs do not have different normalized star formation rate compared to typical X-ray AGNs. And also we compare our results for those X-ray selected heavily obscured AGNs. Our results are also agree with theirs. And from that literature, they find that secular processes instead of a merger are most probable to trigger to trigger those X-ray selected heavily obscured AGNs. However, from our study we cannot simply rule out the relevance of mergers. For example, under the merger-driven coevolution framework, those X-ray detected dogs may be at a later stage where the star formation has been weakened a little bit. So that may explain why X-ray detected dogs show similar normalized star formation rate compared to X-ray AGNs. Also, there are like other studies as I've shown for hot dogs seem to be supportive of the merger-driven nature. So we think merger may play a more important role in more extreme systems, while for our dogs, which are more similar to like typical galaxy populations, the role of merger may play a less significant role. So if we want to have a better understanding, it is better to have more direct observational constraints, for example, on the host morphology or their stellar and gas dynamics. So we can really look at whether those dogs have evidence that they are undergoing merger or they're just after they merge. So here's some takeaway. So we select and categorize the largest sample of dogs in sensitive multivalent surveys to date in the XM SERVS fields. And we find that the dogs are a heterogeneous population. They consist of both AGNs and normal galaxies. By looking at these two aspects, where we find dogs do not show distinctly different supermassive black hole accretion, and we find X-ray detectors, they have similar normalized star formation rate. We think that the X-ray detectors should be considered as extreme type 2 AGNs. One final comment about the study of dogs and the XMM SERVS field is that the XMM SERVS field will have more spectroscopic and photometric coverage soon. For example, the moons and devils, we would have more reliable redshift for our sources, and like Euclid, LSST, we could have we will have deeper photometric information, so we can better constrain their dust properties. And I will leave my my presentation here, and I'm happy to take any question.
When you talk about mergers, what sort of mass ratios are we talking about? Are you thinking about major mergers here, or is it could be like a minor merger contribution? So what sort of?
Yeah, I think simulations primarily focus on major mergers.
Yeah.
I'm not super familiar with like how they did the simulation, but I think the claim was mainly for major merger.
You didn't discuss your X-ray detected or detected dogs. I wonder about the X-ray undetected ones and whether you think it's as heterogeneous as your X-ray detected some.
Mm,
I'll say about it.
at least for X-ray detected ones, we are very certain that each of them must have some significant contribution from AGN. And from those X-ray undetected one, I think those results are their results are kind of like similarly illustrated in the SED fitting plots. I shown before here. Yes, I think since the X-ray detected one, I think they are less heterogeneous than the general population. Though those X-ray undetected ones, they have to be more. They have to be also very heterogeneous, and we actually did some like separate stacking because we from the SED fitting we could have some agent classification results. We could classify agent candidates. We could classify normal galaxies. We also did like separate stacking for those sources. We find that the agent candidates tend to have like a higher stacked X-ray signal, while normal galaxies tend to have less X-ray signals.
Are you suggesting then that among the X-ray undetected population, there are non-AGNs as well?
Yes.
You didn't define what you meant by extreme type 2 AGN.
Yeah.
What is extreme in those type 2 AGN?
Yeah. So what I mean extreme maybe that they in terms of, for example, their colors, because that's how we select those dogs. But we think that their nature is more similar to type 2 AGN.
Where's the dust? Like, what distance is it? Where do you think it's coming from?
Yes. So for example, I think I can show here from the last slide. Yes. So here after we so we think the reason for their high stellar mass is that the galaxy white dust can also contribute to their obscuration. And then after we control for the stellar mass, we also see higher obscuration here. So we think that although galaxy white dust must have some contribution, I think we think the most dominant contribution to their obscuration, if though those were created by dust, is in their nuclear region.
Okay, like parsec scale, like what?
We didn't look too much onto that. I think we could not resolve that much.
Right. I know you can't resolve, but
Yeah,
like,
I'm not sure how like simulations they treat the dust. I think if simulation can have a more can help us understand more about their, for example, their dust formation, how their dust persists, can be very helpful in studying dogs.
great. Thanks, Zhibo again. Or
Sorry, I don't think it can be on parsec scales with these infrared luminosity,
okay.
certainly not the higher ones.
Maybe how often do you see hot dust? The hot dust, like that would have to be probably closer to parsec scale.
There's high column, high dust obscuration. These are a Compton thing.
No, we don't find too many sources with like a similar to Compton cyclic. I think most of them are around like 10 to the 22 to 10 to the 23.
Okay, yeah, that you. Okay,
So they're not as extreme as those.
right.
Others
That-
with
that makes
much
sense.
higher
Yeah.
density.
Interesting. All right. Thanks, Zhibo again.